Welcome to the demonstration of Digital Process Hazard Analysis, or Digital PHA, DEKRA's solution to optimize PHA quality and performance. This is the model that we will be using today. It is based on a CSTR, or continuous stirred tank reactor, which has a diameter of 1 meter, and a height of 2 meters. It is set at ground level and operating at a pressure of 0.3 bar. The design pressure of this reactor is 2 bar and the design temperature is 250 degrees Celsius. It is safeguarded with a high-level alarm and the operator is instructed to close both inlet valves in case this alarm goes off. The chemical reaction that takes place in this reactor is the following. You mix methanol and formic acid and you get methyl formate and water. That's an exothermic reaction, so we will observe some temperature increase. The methanol is fed from an inlet battery limit at 1 bar and 20 degrees Celsius. The elevation of this battery limit is 0 meters, and the composition is pure methanol. Likewise, formic acid is fed from a battery limit at 2 bar and 20 degrees Celsius and the composition is also pure formic acid. The methanol is loaded through a line with a manual valve called MV101, and the formic acid is loaded through a line with a manual valve called MV102. The product is sent to an outlet battery limit at 1 bar and ground level, and the flow of this product is controlled by the level of the CSTR through a level control loop, acting on an automatic valve called LCV101. The name of the control loop is LCO1, and the set point of the level is 1.5 meters, which is 75% of the level of the CSTR. We are considering that the only utility that can fail is the instrument air. So, we are not considering a failure of the stirrer of the reactor in this case. The process is set as a sequence. Don't worry about all this information over here on the left, because that is an internal mini-language that the modeler uses to configure the sequence. We just need to remember that the process starts with a methanol valve fully open, and the formic acid valve fully closed. Then, the operator waits until the level in the tank is higher than 1.5 meters, and opens the formic acid valve in full. The sequence remains forever in this second step, with both manual valves for methanol and formic acid fully open, and the pneumatic valve at the bottom of the CSTR controlling the level of the reactor. This is what the model looks like in Mobitech Modeler. We see our CSTR here, the 2 feed lines of methanol and formic acid, and the product outlet controlled by the pneumatic valve. We have added a couple of charts here, to show the level and the temperature in the reactor, and also a step counter for the sequence. So, as I start the simulation, you see that the reactor starts filling. The methanol manual valve is fully open, and the formic acid manual valve is fully closed, and will remain closed until the level in the reactor reaches 75%. You see here that the control valve at this moment is fully closed, because the level is well below 75%. So, I continue with the calculation and you see now that the formic acid valve has been opened. The reactor has overshot its set point level of 75%, but now it's regaining control of the level. The temperature is rising because we have an exothermic reaction in the reactor. It will also tend to a steady state value. More or less stable now with our level at 75%. The equilibrium temperature seems to be 62.3 degrees. And that is the steady state condition. Let's see what happens if we introduce a deviation here. Let's say, for instance, that we close the formic acid feed, that is now open at 100%. Let's set it at 0%. We see that the level is dropping, but the control is reacting, so we see a little bump over here, but it's recovering. The temperature is dropping because, of course, we are no longer feeding one of the reactants. The reaction is slowing down and we see the temperature going back to ambient temperature. If we open the valve again, we will see the level overshooting. We see another bump, in this case to a higher level, and the temperature is going back to the steady state temperature. This is what Digital PHA does automatically. It generates all possible deviations and it observes what happens in the model. Just as a reminder, Digital PHA operates in 3 different phases. In the first phase, definition of scenarios, the digital tool looks at the model and generates systematically all possible deviations. In the second step or supervision step, the deviations are fed one at a time into the model for processing, and the evolution of the plant is calculated by the model. In the third step, or review step, the results of the model are analyzed by digital PHA and pressures, temperatures, compositions, levels and so on are mapped into final consequences and risk assessment. The software also identifies safeguards, and even tries to recommend some additional actions. Let's create a new project. I'll call it Demo. The client will be Demo Client. The site, Demo Site. The unit, Demo Unit. Revision will be 0 and I'll set the default language to English. We save it and the first thing that we need to do is upload our model. We need to select a few files. Also, our sequence files, and we can save it. Straight away, Digital PHA analyzes the contents of the model and it tells us that there are 9 pieces of equipment and 4 chemical species. Indeed, methanol, methyl formate, water, and formic acid. There are 9 pieces of equipment, our CSTR, the battery limits, the manual valves and so on and so forth, and 8 unknown pieces of equipment. These are basically internal connections and other things that Mobitech Modeler uses for internal purposes. We don't need to care about that. So we have our model uploaded, and then we can generate the scenarios. The system has generated all possible deviations for every step of the sequence and for every equipment type. For instance, we see now that in step 0, while filling up the vessel, a deviation because of instrument air failure, and you have also the name of the variable in the model that will be affected and the value it will take. Likewise, while filling up of the vessel we can see deviation by the control loop ailing open. We have also the control loop failing fully closed. We have manual valve MV101 failing open and MV101 failing closed, MV102 failing open, and so on and so forth. In total, we have generated 50 scenarios for this very simple model. Of course, we can create our new deviation, so we can say, for instance, in the control loop, instead of saying 0 or 100%, we can say that the control loop gets stuck at 50%, at 20%, or at whatever value we want. We need to give our initial step size, let's say 1 second. Runtime period, let's say 10 seconds, we collect the information every 10 seconds and we run this simulation for 200 seconds. That will be a fixed step size. We need to define our potential safety issues, so the things that can go wrong in our scenario. Let's say that we don't worry about backflow. These are the first 3 safety issues, so we disable them. Then we get some concentrations of different chemical species too high. This is intended to capture, perhaps, corrosion problems. Let's assume that we have no problem with concentrations being too high. Then we get levels too high in the reactor. Yes, indeed that can be a problem. By default, is set to 10 meters, but we know that our reactor has a height of only 2 meters. So, we need to set that level up. Level too low. Yes, indeed, that can also be an issue. Let's adjust it to 0.1 meter. Pressure to high 100 bar. Let's limit that to 3 bar. Pressure too low, 0. That's okay. Temperature too high. Instead of 300 degrees, let's say that our system is rated at 250 degrees Celsius. And likewise for the reactor. We save it and we have defined our safety issues. We can also define our potential operational upsets. Operational upsets are very similar to safety issues. However, they are not flagged as hazardous conditions. Perhaps we can consider things like product out of specification, or production too low, or this type of things. We are not setting any here. Let's disable the 2 that are already generated automatically. Now we have to define our potential safeguards. We know that we have a high-level alarm in the reactor. There it is. So, we enable this safeguard and it provides a risk reduction by default of 0.1, which seems reasonable for this type of safeguard. That is it. We have now completed our preparation. We just need to hit simulate and then all these 50 scenarios will be sent one at a time into the modeling system to perform what we have just seen, introduce a deviation, and observe what's happening. Once all the simulations are completed, we are asked to answer some environmental variables. In this case, if there are water courses or water bodies nearby. Let's assume that yes, there is one. The value of the asset, because that has an impact on economic damage. Let's say that it is below 100,000 euros. And there is an ignition source near the point of release? Let's assume that yes, there is an ignition source near the point of release. We save it and that's our result in the form of a HAZOP table. Very similar to those that we are used to seeing in HAZOPs and other types of PHA. Here we have for every step in the sequence, the failure, the deviation or scenario that generates the consequence, the final consequence frequency, the risk assessment before safeguards, and the safeguards that have been identified. We also have the risk assessment after safeguards, the recommendations and the risk after recommendations. Of course, there are some dynamics in here. For instance, in the first scenario we have a high-level alarm, and the system recommends to introduce also a high-level interlock to reduce our risk to an alarm level. But we could go back to the preparation phase and include this interlock as an existing safeguard. That's a high-level interlock in the reactor. There it is. We can edit it and we can say that it is existing, so it's not disabled, and we can even say that it has a risk reduction factor of 0.001, so we could say that this is like a SIL 3 level. We save this safeguard. Then, we go back to the supervision phase and recalculate the results. We observe that the interlock is no longer a recommendation. It has become a safeguard, because we have activated it as a safeguard, and the risk has been reduced from not tolerable before safeguards to an alarm level after safeguards. Or, in another case, already to tolerable, and, of course, the recommendation no longer appears. That's a way, let's call it a traditional way to look at the results, but the results are saved in a structured database. Therefore, we can look at safety issues like this. Simulations raise two safety issues, level too high and temperature too high. Then for instance, if we look at level too high, we can identify which steps and deviations lead to this condition of high level. And furthermore, we can see and even download the history of the parameter. In this case, the history of level inside the vessel. Likewise, we could go to temperature and see the evolution of temperature inside the reactor in this deviation. We can also look at operational upsets in a very similar way, or we can look at simulation results and then we see all the scenarios that have been simulated. In this example, all have been simulated successfully, and we can see in which scenarios we have observed safety issues or operational upsets. Let's look at this case, and it will show us the safety issues that were activated. And again, we can look at the detail and we can even download the detail. So, we have multiple ways to access the information, including of course the, let's call it a traditional table, which can be exported to an Excel file for further analysis. And once we are happy with this digital PHA, we can upload it into Dynamic Risk Register, another of our process safety solutions. There is another recorded demonstration of the Dynamic Risk Register, should you be interested. That's it for today. I hope you have found this solution helpful, and if you're interested in learning more, please do not hesitate to contact us.